Welcome to EDU World Space.
We know that optical fibers are thin cylindrical cables which are used for communication and they carry the information by total internal reflection without any losses. Now, such kind of optical fiber, if those are bent, then due to that bending, it may have or it may lose the data because the angle of incidence at those bent, it may not be equal or greater than that of critical angle, so then that data will be lost. So how much this bending radius, so if I consider here this is an optical fiber of diameter d, and suppose it is bent, and this bend radius, let me say it is as r here. So with what radius that we can possibly bend this so that the information or that rays will not be escaped through the optical fiber, that we want to find out here. So for this, now let us consider here a ray which get incident at a point B on this optical fiber at one of its bend point, and this ray, suppose it is at distance x from this lateral side of an optical fiber. Then in this particular figure in triangle, this sine, if we take here sine of theta I in first case, that would be equal to, here I can write this opposite side which is r plus x upon hypotenuse. We have this is r and this is d, so I can write this is r plus diameter of that optical fiber d. Let's say this is equation number 1. Now by this I can able to find out theta I in first case, that is equal to sine inverse of r plus x upon r plus, we know that sine theta being a strictly increasing function of theta in the range of 0 to 90 degree, the minimum incidence angle will corresponds at x is equal to 0, and that is the ray which is very close to this surface. Let me show here, it will be very close to this surface like this. So where x is almost 0, so this ray will be get incident somewhere here, and suppose that makes an angle theta I here with the normal to this surface. So in this particular figure, if I say this is C point, then if I take sine of theta I, so that will be equal to this r upon r plus d. Let's say this is equation number 3. Now applying Snell's law at point C, by for total internal reflection, as we know that theta r, this angle of refraction, that must be theta r, that must be greater than that of 90 degree. So applying Snell's law at point C, uh, for this particular condition where theta r should be required, that is greater than 90 degree, n of sine theta I, that is equal to, as it is air medium, so its refractive index is 1, so I can write this is sine of theta r, and here this theta r, that must be greater than that of 90 degree. So therefore I can write this as n sine of theta I, that should be greater or equal to that of 1. So from this I'll get this n is equal to, n is greater than or equal to 1 upon sine of theta I. So let's say this is equation number 4. Now the value of sine theta I we know from equation number 3. Putting this value over here, we can write n should be greater than or equal to 1 upon this r plus d, which I can simplify and rewrite as r plus d upon r. And as we want to find out r, so let us further simplify this relation. N is greater than or equal to r upon r is 1 plus d by r, and if I take 1 to this side and if I find for r, then that will be r is greater than or equal to, I can say, d upon n minus 1. So this the minimum bending that should be there so that the rays will be totally internally reflected in optical fiber and there will be no loss. Thank you.